Hi, and welcome back to Basic Logic, an Open Introduction. I'm Dr. Nick McGinnis. In the last video, we started Chapter 7. Part 2? We did a bunch of Chapter 7 from For All X, the Lorain County Remix, an open source logic textbook that you can download for free online. It'll help you follow along this course and do exercises, so I strongly recommend you have a look at that textbook. Now, in Chapter 7, we were using truth tables to demonstrate that sentences, sets of sentences and arguments had certain properties. For example, you can use a truth table to show that a sentence is a contradiction or that an argument is valid. The methods were pretty simple. You completed a truth table and then you verified the values underneath the main logical operator, typically. So I also introduced to you the idea of a shortened truth table, where typically you would assume the opposite of the thing you're trying to prove and derive a contradiction. So I'm going to talk a little bit more about shortened truth tables, and then actually we're going to be done for Chapter 7, and we're going to be moving on to the more powerful system for verifying properties of sentences and arguments, the derivation system. Now when I teach this class, I sometimes bring in funny little logical jokes. So this is from the webcomic SMBC, Saturday Morning Breakfast Cereal. And the statement is, if you're not part of the solution, you're part of the problem. In symbolic logic, it says that's if S, then not P. It says that given the law of contraposition, you can get the new statement, if you're not part of the problem, you're part of the solution. Leading for someone to say, well, you did nothing all day. I'm helping solve a race problem. But if you're not part of the problem, part of the solution. Is this argument valid? Why or not? So consider like a little bonus exercise to do after the difficult exercises from the last practice one that we concluded the last video with. Given that the contraposition is a law, the argument is valid. Okay. So how do we use these partial truth tables in every case? I showed how to use them in some cases, but more generally, all we need to do is to, in the case of, say, a tautology, is to show that there's, at least it's possible that, so for a tautology, of course, on the main logical operator, what we're supposed to see is a nice column of t's. So under the main logical operator, if it's not a tautology, you should see at least one f. So here's what you do. You assume f. Either you show that it's possible or you derive a contradiction. We don't require a complete truth table. We can just write, we assume the opposite. Is it a tautology? It's not going to be useful to assume t because if it is a tautology, there'll be t's everywhere. What we're saying is that if it's a tautology, there should be no f's at all. So what you do is you write f underneath the main logical operator to determine whether or not it's possible. If it is possible, you've shown it's not a tautology. If it's impossible, you have a contradiction, and you've proved it, in fact, is a tautology. So the following sentence below is not a tautology. Right? We have, if u and t, then s and w. So this is pretty obviously a contingent sentence. And we know this because it is possible for the sentence to be false. So this sentence is contingent. Why don't we look at an example where the sentence is in fact a tautology? Let's look at a very simple tautology, one we maybe already looked at. How about if p, then either p or q. The main logical operator, of course, is the if-then here. So what we're going to want to do is assume f, because we're asking, is that possible? Now, for this to be false, the antecedent has to be true, but the consequent false. Underneath the main logical operator, the consequent. So what we need is t, f, for this to be f. For this to be false, what we need is both sides to be false, because it's a disjunction, false, false, false. Now, do we have a contradiction here? Sure we do. P has to take the value false, and has to take the value t simultaneously. We've already done this example, I think, in an earlier video, where you see how assuming the opposite in a shortened truth table can prove that a sentence has the property. So to show something is not a tautology, you produce this kind of partial truth table where the main logical operator is false and there's a consistent truth value assignment. Now, showing that it's not a tautology doesn't prove anything else. It just shows it's not a tautology. It could still be contingent. In fact, it could also be a contradiction. If you want to show something is not a contradiction, produce a partial truth table where the main logical operator is true instead of false, and there's a consistent truth value assignment. There's no contradiction there. If something is not a contradiction, it could be a tautology, it could be contingent. So, the way it's going to work is pretty simple. Sentences can be tautologies, contradictions, or contingent. If they are tautologies, then assuming false would produce a contradiction. If there's no contradiction, it could still be contingent, or it could be a contradiction itself. So if you ruled out a sentence as being a tautology, you don't know whether it's contingent or contradictory yet. You still have to check that. The next thing to check would be to see if it's contradictory. If it's not contradictory, then it's contingent. So let me just go over this again, because you have binary truth values, but you actually have three potential properties here. So a sentence could be a tautology, it's always true. It could be a contradiction, it's always false. It could be contingent, which is sometimes true, sometimes false. So the way this works roughly is that if you prove that something is not a tautology, all you've done is eliminate. So if it's not a tautology, it could still be either of these things. Likewise, if you prove that it's not a contradiction, it could still be either of these things. So if you test for a tautology and it's not a tautology, it could either be a contradiction or a contingent. Then once you rule out that it's a contradiction, you show that it's contingent using shortened truth tables. So to show that something is contingent using a shortened truth table, you actually need to verify whether or not it's a tautology and whether or not it's a contradiction. So you need to do both using a partial truth table. If you do the full truth table, you're actually checking for all three. If you do the full truth table of a longer sentence instead of a partial truth table, then looking underneath the main logical operator will tell you whether it's a tautology, a contradiction, or a contingent sentence. If it's a tautology, the main logical operator will be a full column of T's. If it's a contradiction, the main logical operator will be a full column of F. If it's contingent, it'll be some of both. But if you're using a partial truth table, all you're showing is that it's not one of these things, and it could still be either of the two other ones. That's an important thing to remember. Knowing is half the battle. Okay. If something is in fact contingent, you should be able to produce a two-line truth table, of course. But just remember that if you prove something's not a tautology or not a contradiction, you haven't shown what it in fact is. So, how could we do shortened truth tables for some of the other properties? For example, logical equivalence. Well, logical equivalence you can test by showing that a one-line truth table with one sentence has value t and the other one is false. Otherwise, we can show equivalence by showing that the biconditional is a tautology. Then that just reduces to the case for checking whether or not something's a tautology, right? Let me just say that again slowly. Two sentences are logically equivalent if their biconditional is a tautology, which reduces the problem of logical equivalence to what? The test for something being a tautology, which is already covered. Now, a set of sentences, many sentences, is consistent if there's at least one line where they're all true. So I just give them T's under all, and I see if there's a consistent truth value assignment. However, if they are inconsistent, a full truth table will be required. Why is that? Think about it. So, okay. So here's kind of a table for partial truth tables and the kinds of tests you need to do if you're going to do short truth tables instead of the full ones. So if you're going to be testing for the presence of the property and presence and absence of the property. So is it a tautology? Right, then you're going to want, you can do a complete truth table with all T's. If it's not there, you do one line with the main logical operator is false. If it's a contradiction, complete table all F's. Test for absence of the property contradiction, one line with the main logical operator T. Right, so you kind of see how this works. So if you want to use partial truth tables to prove something, testing for the presence and absence of a property is just kind of have a look at the table. Now you know how to do it. I'm just kind of rushing through this because it's not actually that important in the grand scheme of things. It's actually pretty straightforward how to apply partial truth table tests to determine properties. So have a look at that table, and I have some exercises coming up so you can refer back to this table. Okay. Right. So we can all define these notions in terms of each other, right? For example, right, I've already said we can define logical equivalence in terms of the tautology because two logically equivalent sentences are a tautology if they're joined together by a biconditional. We can also define them in terms of consistency and inconsistency of sets of sentences. In the trivial case, a sentence P is a contradiction if the set containing only itself is inconsistent. It's a tautology if it's inconsistent, if the negation is inconsistent. If it's neither, then the set containing P is contingent. Interesting. But it's a bit of a trivial case because there's only one member of the set. Two sentences P and Q are logically equivalent if the set denying the biconditional joining them is inconsistent. Mind you, it's not enough to show that the set of them in a biconditional is consistent. We have to show that it's a tautology. And a argument, right? Argument test for validity, a set of premises and a conclusion will form a truth functionally valid argument only if the set comprised of what? The set of sentences comprised of the premises and the negation of the conclusion is inconsistent. Again, these kind of equivalencies or the fact that you can test for various properties using each other is an interesting feature of SL. It's not going to be figuring as really primordial in a basic logic class. However, it's important to understand that these things are kind of intertwined, right? That I can verify for equivalence using a tautology. I can verify for validity using the concept of inconsistency. There's my next slide. Okay. So here are, let's kind of put it all back together. So here are a couple of arguments in our natural language English. And then your task here would be to translate them to SL and then use a truth table in whatever way you like. It could be a short truth table, it could be a partial, it could be a full truth table. You could use the conditional check, you could use the consistency check, whatever you like. The idea here is you're going to start with the argument and see if it's valid, not if it's sound. Soundness has to do with the premises are true in the world or not. But just see if the argument is in fact valid. Okay, so pause the video, have a look at these arguments, and let's see what your translations look like. Okay, so let's look at these arguments. First argument. If space is infinitely divisible, then Zeno's paradoxes are compelling. So that's obviously premise one. Zeno's paradoxes are neither convincing nor compelling. Therefore, space is infinitely divisible. All right, at a glance, this argument doesn't seem valid to me. But let's start by translating it to SL. The one tricky sentence might be the second premise. Zeno's paradoxes are neither convincing nor compelling. A neither nor statement is typically a negated disjunction. So we have Zeno's paradoxes are not convincing and Zeno's paradoxes are not compelling. So why don't we have a look at that argument? So let's start with the first premise. Right? If space is infinitely divisible, is that S legible? Okay. Chose the blue one. Then Zeno's paradoxes are, what is it, compelling? Zeno's paradoxes are compelling. So why don't we just use C? Now, I tried to trick you by using convincing and compelling, which both start with C, so you might be tempted to, translate it in a weird way. But actually, we should consider them as two separate atomic statements. So premise one, if space is infinitely divisible, then Zeno's paradoxes are compelling. Premise two, however, it is not the case that they are convincing or compelling. Why don't I put V or C? Uppercase V, they're not convincing nor compelling. And conclusion, S, space is infinitely divisible. So now what we're going to do is try and see if this argument, find out if this argument is valid, now that we have it translated and presented in standard form. Premise one, premise two, conclusion. All right, so how would we do this? Maybe we should have a shortened truth table. So I'm going to start over here. If S, then C, premise one, neither V or C, and conclusion S. What we want to find out is it possible to have true premises and a false conclusion? So why don't we make the conclusion false and both premises true, and we'll see if there's a contradiction here or if there's a way in which all the premises are true and the conclusion false. The shortened truth table way, the idea here is to recover a truth value assignment that is consistent that every atomic sentence has a T or F without contradiction, such that this assumption, true premise, false conclusion, can be maintained. So, is there one such truth value assignment? The first thing we should do here is look at the values of atomic sentences that have already been assigned and then repeat them wherever they need to be. In this case, S has been valued at F already. So I'm going to put F over here under the other S. Good. Is there anything else we can do at this point? I don't think there are any more forced moves. What we just want to find out is it possible to have true premises and a false conclusion? Now, C could either be true or false. So let's forget that there are no more forced moves here. But this is true, and therefore that means this negation must be false. So we actually have some forced moves over here. What I mean by forced moves is things that we have to write. There are cases where this is open. This could be true, and C could either be true or false. So I don't know yet. It's a minesweeper mine where I have to put a question mark on it. Over here, I have some forced moves, because if this premise is true, the main logical operator not has to be true, then the secondary logical operator here, the or, has to be false. And if this is false, then V has to be false, and C has to be false. Now I've recovered a value for C. Let's put it over here. Now, is this consistent? Are there any contradictions? No, there aren't. There are no contradictions in this truth value assignment. Right? Is this premise true? Yes. False, false, true. Is this premise true? Yeah. False, false. Therefore, not as true. So the premises are true. There's no contradiction, and the conclusion is false. So I keep wandering on screen. So is it possible to have true premises and a false conclusion? The answer is yes. You can have true premises and a false conclusion. So this argument is invalid. If I wanted to, right, of course I could put the arrow here and do a different kind of truth table and do the arrow test to find out if this is a tautology. And of course I would find out that true, false, false. This and is true, because true, 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 true. And this conclusion is false, true, false, there's no contradiction. So the conditional joining premises and conclusion is not a tautology. So the argument is not valid. Second argument. Where's my eraser? This is the boring part. Hey, when does a joke become a dad joke? When it's apparent. Okay, Newtonian physics can't be right if Einstein is right. But Einstein is right if and only if space is non-Euclidean. So space is non-Euclidean, or Newtonian physics is correct. Okay, so here we have no conclusion indicators like the other one. But since I wrote the example, I can tell you that the last sentence is the conclusion. So let's try and get these in standard form. I'm going to only maximize the video after I actually write these down. So let's do it. Newtonian physics can't be right if Einstein is right. Now the if is kind of in the middle of the sentence. So what's going to be the order here? We have Newtonian physics can't be right, and then Einstein is right. What are we going to do? How about if Einstein is right? So premise one, if Einstein, then not Newton. So if E, then not N. Whereas N stands for Newton is right, E stands for Einstein is right. Way back I suggested that if you have a negated English sentence, you should translate it with a negated SL sentence with that big negation there. So we have, if Einstein is right, then Newtonian physics can't be right. In English, we often say things such as where the antecedent comes later in the sentence. Newtonian physics can't be right if Einstein is right. Which is really just saying we can front load that if Einstein is right. If you don't believe me on this one, instead of E, then not N, just flip it around. Think, if not Newton, then Einstein is right. But that actually means something quite different. So we're going to keep the if E, then not N reading. But Einstein is right if and only if space is non-Euclidean. This is kind of a pretty wonky science example. Non-Euclidean space-time roughly means that space is a curved surface of some kind as opposed to the flat Euclidean, plane or like a three-dimensional kind of solid that we're used to. So non-Euclidean physics just has to do with non-Euclidean geometry has to do with like geometries of curved surfaces. You can Google all this stuff. The nice thing about logic and its content neutrality is that you don't really need to understand anything the argument is saying. It doesn't matter if you don't know what non-Euclidean space is. All you need to know is how to translate kind of chunks of English into atomic sentences. But Einstein is right if and only if space is non-Euclidean. So what are we saying? Well, we have E for Einstein, if and only if, so we have a double arrow, space is non-Euclidean. Non-Euclidean, should we translate that with a negation? It is not the case that space is Euclidean. Sure, we can do it that way. How about it is not the case, so we already have an E. How about it is not the case, how about S for space is non-Euclidean? Not the case that space is Euclidean. So conclusion, space is non-Euclidean, Newtonian physics is correct. So either or Newton is correct. There we go. That's my translation. Now at this point, because we have a pretty good translation, we can kind of ignore the specifics of the argument because we're interested in the validity of the logical structure and not any kind of debates about Newton, Einstein, Euclid, general relativity, the curvature of spacetime, Lobachevskian manifolds, Riemannian spacetime. These are just physics buzzwords that I don't really understand, but I've heard smart people say them. So here's our argument. If E, then not N. E, if and only if not S. Therefore, either not S or N. Does this look valid? At a glance, maybe. But how do we prove it? Well, let's use a shortened truth table again. So, premise 1. If E, then not the case that N. Premise 2. E, if and only if not S. Conclusion. Am I running out of board space here? Is this legible? Adjusting the monitor. It's pretty good. Therefore, conclusion, either not S or N. Now this is actually pretty complicated, but we have to remember the procedure for the shortened truth table is simple. In this case, I'm just going to assume the premises are true and the conclusion false. That's going to be my informational input for this test. To see if something is valid, I'm going to assume true premises and a false conclusion, which means that I can input a lot of data into the premises and conclusion. I have a lot of T's and F's that are inputs, and as a result, probably a lot of interesting downstream consequences. So what's the main logical operator here? F, true premises, false conclusion. So the negation is false. False negations are great for us because it forces a lot of moves, because a negation is only false in one case. What is that case? That both sides are false. So now I have recovered values of the atomic sentences. I know that in order for the argument to be invalid, i.e. for the conclusion to be false, that the value of S everywhere it is here must be T, and the value of N everywhere it is must be F. Well, that's good. However, I'm not done inputting my basic assumptions, which is that the premises are true and the conclusion false. So now I have true premises, false conclusion, and I've also have some forced moves here. N has to be false, and S has to be true. At this point, again, I'm not even thinking about what S and N and E represent. I'm just thinking about what are the forced moves given the input I have, which is true premises, false conclusion. So I'm just filling in the details here. So we have a negation operator here, so if N is false, then not N is true. We have another negation, so, right, if S is true, then not S is false. And let's see here. What are the values? Is it possible to have true premises and a false conclusion? Let's see. The only value I have left is over here. Now, this is an if and only if, a biconditional. A biconditional is only true when both sides have the same values. So, if this side has a value of F underneath the negation, then E is also going to have value F for false, false, true. That's a forced move that needs to happen for my premise to be true. So now I know the value of E over here. Alright. Now I have the following completed shortened truth table where I have true premises and a false conclusion, where E has the value of F. That's false, true, true. So this one doesn't have a contradiction implicit in it. And so we're fine here. Is there a contradiction here? No, that's fine. And is there a contradiction here? No, that's fine. So we haven't found a contradiction. We can have true premises and a false conclusion again. So this argument is invalid. Let's just do that again. We have assumption. Is it possible to have true premises and a false conclusion? Sure it is. If I assume the conclusion is false, I'm forced to assign these following values. S is true, N is false. Now, if I assign these values here, I find that I can maintain these values while having true premises. Right? S is true. That means not S is false. Right? Why do I get this true? Because over here, right, on the disjunction, right? So this means E has to be false, 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 true. E has to be false, and if the antecedent is false, and the if then, so this argument is invalid. There's a way in which this argument can have true premises and a false conclusion, so it's not valid. What is that way? When E equals false, N equals false, and S equals true. On that assignment of truth values to the three variables here, we see that the argument is not valid. And we can go back and think a bit about the logical structure in English of Newton and Einstein and all those things, but why bother? We proved it as a function of logic. In fact, it's going to be invalid no matter what we replace E and an S with. So that's the shortened truth table version of this problem. So notice that argument 2 might be valid if we actually had a slightly different reading of premise 1. I had it as, if Einstein is right, then Newton can't be right. But of course, if we reverse it, we say, if Newton isn't right, then Einstein must be. Right? Because kind of the only if condition, the argument actually might come out as valid. So for a bonus exercise, you might want to look at that one. Now, we have more problems here. Again, at this point in the class, things are much less conceptual than they are practical. So I've done a couple now. There's 3 more here. Maybe we should try and translate them. And by we, I mean you, not me. Do the following 3, translate them, and check to see if they're valid using a truth table, a long one, or a short one. So pause the video and work on those. And if you liked them, and you paused and did, I have more. Let's do more. You should also look at Chapter 7.5, parts A through J. Just do as many as you can here. If you're not sure about your answers, ask a friend or email me. There's way more than I could comfortably do using YouTube videos. Maybe if I have time after the lecture, I'll actually make promises I can't necessarily keep, but maybe I'll have like a bonus video of supplementary answers, or if you send me an email at nickmcginnis@gmail.com, I'll take some requests and I'll do some answers on the board. All right. So here's a little bit of fun bonus material. All these technically are valid arguments. Argument 1 is what's known as explosion in classical logic. The reason contradictions are bad is actually anything follows from a contradiction. Well, I'll prove that more formally a bit later when we do derivations, but you can check for yourself, right? We've already talked about special cases of validity. If the premises can't all be true, then you can't have true premises and a false conclusion, therefore the argument is technically valid. If the consequent is true, if you look at number 2, it follows that all conditionals using it are true. So if for any atomic sentence B, the conditional if A, then B will be true. But that's just a conditional, so maybe it's not that big a deal. These are called paradoxes of material conditional because some philosophers think that they actually pose a pretty significant challenge to the interpretation of the regular truth table of the conditional as representing the if-then of ordinary language. If the antecedent is false, all conditionals using it are true, right? If Facebook existed in 1886 and I'm a walrus, technically a valid argument. If not A, I can derive if A then B. So these are all kind of weird. Now, one answer to these paradoxes, these kind of weird cases of validity, is that they only appear counterintuitive to us because in our everyday reasoning and language, English is actually governed by rules that go beyond logic. These are called pragmatic rules. In linguistics, we typically think of language as having three levels. The first level, the most basic level, is syntax. That's what makes language grammatical or not. We've already had a definition of syntax in SL. Syntax is what makes a sentence of SL grammatical or not. The difference between P and Q and PQ and bracket bracket if, which is not a sentence. Likewise, I am standing is different from standing. Am, I. Well, that's actually sounds like something Yoda would say, but like cat B, dog bit A. That's not a sentence. So syntax is the first level. Semantics is the next level. So if syntax gives you the rules for constructing a sentence, semantics tells you what the sentence means, what it's about, what it refers to in the world. The last level is pragmatics. So pragmatics is what is implied by a sentence, or what you can infer from a sentence. That goes beyond what is strictly speaking said. Now, pragmatic rules in English might be something like, be relevant, assert the strongest information you have. Now, logic doesn't have pragmatic rules. So some people say these weird paradoxes are not objections to logic. They're observations about the way we use language in particular contexts, which are governed by pragmatic rules. So, for example, what do I mean by a pragmatic rule governing discourse? If I ask someone who won the race, and they say, it was either Bob or Mary, I can infer that the person is not sure between Bob and Mary who actually won. It was one or the other, but they don't know. Now, from a point of view of logic, this answer is strictly speaking true. If he knows that if the person I asked knows Bob won and says either Bob or Mary, well, what they said was technically true. It was either Bob or Mary, given that he knows it was Bob. But why would somebody say that? Purely logically speaking, saying something true doesn't mean the same thing as saying it in English in a way, because English is governed by stronger pragmatic rules. Right? I would never answer either one or the other if I wasn't sure. Even though technically speaking, logically, saying it was either Bob or Mary when I know Bob won is logically true. So logic, one of the reasons it's kind of hard to grasp sometimes is that you actually have to think a bit less. It's not that logic is hard, you need to think more and harder and bang your head on the desk. It's that you actually have to kind of forget about all the rules that usually govern conversation. You heard it here first, folks. Dumb yourself down to understand formal logic. Here's some more fun problems for the conditional. These are all kind of cribbed from Graham Priest's great book, what is it called? An Introduction to Non-Classical Logic. And these are all perfectly valid inferences, right? If you open switch A and switch B, light C will turn on. Hence, either if you open switch A, light C will turn on, or if you open switch B, light C will turn on. So that obviously doesn't work because they could be working together. Anyway, I don't know if I want to go through all these and explain them because we're already at 33 minutes. So these are interesting paradoxes of the material conditional. You can kind of Google paradoxes. You can read them. They're interesting, and I like talking about them because they're kind of fun little problems in classical logic, but I'm not, they're not really intrinsic to what we're doing here. All right, yet more problems. How many problems did I put here? If it does not rain tomorrow, I'll go for a picnic. Hence, if it does not rain tomorrow and I'm killed in a car accident, I'll go for a picnic. Antecedent strengthening. So again, that's valid, but intuitively it seems a little weird. So, of course, right, there's a gap between logic and ordinary language in all possible reasoning contexts, and there's a lot of very technical work out there trying to address these apparent paradoxes. The pragmatic solution only goes so far, and I just kind of want to point at these because if you're interested in formal logic, it's not like logic has been solved. There's still great work to be done. So if you want to pursue a career as a logician, there are unsolved problems that you can work at here. What I just want to stress is that all formal systems have limitations. And when we try to model and explain more complicated phenomena like natural language, you're going to bump up against the limits of an artificial language like logic. But formal systems are very powerful because they're simplified, not despite of their simplification. All of computing technology exists just thanks to logic gates, which are roughly the 16 logic truth tables we looked at a few videos ago. So logic as an abstraction, as a simplified artificial language, has strengths and weaknesses. All right. So that's all the time we have for chapter 7. Next video, we're going to be looking at the derivation system in sentential logic, which is a more powerful system, not just for testing the properties of sentences and sets of sentences and arguments, but for actually generating in a more creative way new sentences from sets of premises. You'll understand what I mean. Meanwhile, I think there's a logical error in this XKCD strip. So have a look at it, see if you can figure it out.